Okay. Sorry about the technological problems. That seems good now. If everyone can hear me, that's good. So I was acknowledging and paying my respects to the Palau peoples, the traditional custodians and caretakers of the land that we're meeting on. And I wanted to also extend my respects to the Aboriginal elders, past, present, and emerging, and to acknowledge the Tasmanian Aboriginal community who continue to care for our country. So Tom Williams here started as a postdoc in ACEAS based at UTAS in January this year, and I think he may have been the very first postdoc. I'm not sure about that, but one of the first anyway. And he holds a PhD from the University of Cambridge, and he's also worked briefly for the British Antarctic Survey. And before joining ACEAS, he was a postdoc at the University of Florida, where he worked on Southern Ocean paleocirculation. And yeah, Tom's first months at ACEAS involved quite a pivot of research focus, because he was meant to sail on a Canyons voyage, which was canceled, but that pivot has actually worked to his advantage, as you'll hear. So he's dug into some archive materials from the Cape Darnley region, and as you'll hear, this is leading some really interesting work on the links between climate and ice sheet behavior. And I think you'll find that there's a lot of potential in that work for like collaborative efforts within ACEAS that could have real impact. So I hope you all enjoy Tom's seminar, which is titled, "What Can Earth's Past Tell Us About Our Future? Mid-Pliocene Warm Period." Take away, please, Tom.
Thanks very much for the introduction there, Anna. Yeah, and I hope that you'll find this talk interesting. As I said, there's a lot of potential overlaps with other people in ACEAS, so please do get in touch if you feel invigorated about this. So I'd also like to thank Laurie, Adele, and Alyssa for inviting me to speak, and also to all of you here for coming along. So I'm really excited to get a chance to talk to you today about some of the ongoing work that I'm doing, investigating what we can learn from an interval in Earth's past known as the mid-Pliocene Warm Period. And this period has been suggested as a potential analogue for our future climate in the not too distant future. So first of all, then, I'm just going to spend a bit of time introducing what we can do as paleoclimatologists, or what we do as paleoclimatologists, and how our work can inform us about the climatic changes that we are experiencing today. And then I'm going to go on to talk a little bit about the work I'm undertaking as part of ACEAS, and I'll take you through some of our very preliminary results. So what insights can we gain then from studying Earth's past climate? Well, first and foremost, any work we want to do looking at changing climate is going to need some kind of baseline against which to compare. And so by extending records back beyond the instrumental era, paleoclimate work helps us provide that baseline. So here, if I just get my laser, here's an example actually from the latest IPCC report, showing temperature changes going back over the last 2,000 years. So on this graph, the modern era is here on the right, and time's going backwards this way. And then on the y-axis, we have temperature anomaly relative to the pre-industrial period. And so obviously this helps contextualize the recent climate change kind of warming that we've been seeing in the last century, and puts into perspective forecasts of future climate change as well. So paleoclimate studies can also allow us to investigate drivers of climatic variability through time. So by understanding how different aspects of the climate system have evolved through time, that allows us to pick apart how individual signals might be driving climate variability. So here's just another example from the latest IPCC assessment, just showing kind of how a knowledge of individual natural climate variability and climate drivers through time, which is kind of represented here by this green line, this green shading, can help us pick apart natural climate variability versus anthropogenic climate change. And so another kind of useful aspect, I guess, of paleoclimate work is we can look at past periods of climatic change, or we can investigate interesting times in Earth's climate past, where maybe there are different boundary conditions to the modern. And so we can use these intervals to interrogate our climate models. And so a really good example of that is the Paleoclimate Model into Comparison Project, or PMIC. And so one of the aims of PMIC is to test our climate models against different background climate states. And so I picked out this recent example, which is just showing productivity change during the peak of the last ice age relative to modern or pre-industrial. And the model output is the sort of shading in the background, and then overlaying the paleo observations. And I think, yeah, you can kind of see how this would be useful to test in testing the effectiveness of our models, maybe highlighting areas where they might need more work, and also actually like understanding more about our past climate history. And so, as with all things in science, in real life, of course, it's a lot more complicated than that. Different aspects of our climate system don't operate independent of one another, and there are complex feedbacks in the climate system. And actually, as paleoclimatologists, a lot of our time seems to be spent trying to pick apart these drivers versus responses in the climate system. So hopefully I've just given you a little overview, a little intro into paleo climate for those of you who aren't so familiar. But moving on to talking about some of my work with ACEAS. So one of the projects I'm involved in, working on, is investigating the environmental response to a past period of warming known as the mid-Pliocene Warm Period, which has been suggested, as you might gather from the title of my talk, to represent an analogue for near future climate change. So, as the name kind of might suggest, the mid-Pliocene Warm Period was an interval of comparative warmth in our recent geological past, and it occurred approximately 3 to 3.3 million years ago, which is actually the last time Earth's temperatures reached those expected in the near future and the mid to high-end emission scenarios. So here again is another figure from the IPCC's latest assessment, showing temperature anomaly again relative to pre-industrial through time. So on the y-axis here is the temperature anomaly relative to modern, and then on the x-axis we have a variety of x-axes ranging in their length of time that they cover. So on the right-hand side here, you can see we have our recent warming trend in black, and then moving forward into the future we have expected warming under different emission scenarios. If we move across to the left, we have now looking back at Earth's temperature through the last 800,000 years or so, or 800,000 years. And you can see that we have these periodic cycles of cooling and warming and cooling and warming. I guess it should go the other way, cooling and warming, cooling and warming. And these are all sort of part of the natural variability that we investigate as paleoclimate scientists. And so this variability, we think, is being driven, or the timing of this variability is being driven by regular changes in the Earth's orbit around the sun. Moving even further back in time, we're now looking at length scales of millions of years, tens of millions of years. And you can see sort of highlighted just here the mid-Pliocene Warm Period. And so that's the period that I'm investigating. And just to give a sense of kind of the importance that's been placed on this period, to kind of highlight the fact that this is actually like figure 1 in a technical summary of the IPCC's latest assessment. So obviously a lot of emphasis is being placed on this time period. It's increasingly being used as a benchmark against which to compare future climate projections. Okay, so what then makes the mid-Pliocene warm period such a good analogue for potential future climate change, near future climate change? Well, the climate back then obviously was very similar to today, or similar to that predicted for the second half of this century at least. So we had CO2 ranging between roughly 350 and 450 parts per million. Just for a little bit of context, we're currently sat around, last year's average was 418 parts per million, and pre-industrial values were 280 parts per million. So we're really rapidly approaching the kind of upper limits of that range. So we also have warmer temperatures than pre-industrial. So globally, the average change is somewhere between 2 to 4 degrees warmer than pre-industrial. And again, just for context, where sorry, something just popped up on my screen. There we go. Sorry about that. Yeah, and just for some more context, yeah, we're currently sitting around 1 degree C warmer than pre-industrial. So they're kind of obvious things that make this a good analog. What else? Well, we're not going back so far in time that paleogeography is dramatically different from what it is today. So, you know, the continents haven't shifted position or anything like that. If you were to be transported back 3 million years, you would probably recognize what you're looking at. And also, really importantly, the orbital configuration, so where the Earth was situated in its orbit around the Sun, at times was very similar to today. And so by studying that period, we can kind of disregard orbital changes as being a factor potentially. Okay, so that all makes this a really interesting time period to study. And what makes the mid-Pliocene especially interesting to me and to other researchers was what was going on with sea level at the time. So here's a figure showing reconstructed sea level over the last 3.5 million years. And actually now we're going back in time. So the modern is actually on the left of this figure. And we're going back in time to here's 3.5 million years. And this graph is showing change in sea level reconstructed relative to the modern value. So I've just put a black line through the zero change relative to modern. And we can see that sea levels, again, vary through time on these glacial and subglacial cycles as part of these natural climate variability. But if we look back at the mid-Pliocene Warm Period, which is just this area, this period here that I've highlighted, we see that at times sea level was actually up to 15 meters higher than it was today, and actually some estimates a bit higher than that. And so obviously this is happening in a background climate that we're expected to experience in our, geologically speaking, near future. And so to achieve this 15 meters sea level rise compared to today, this suggests that we must have lost most of the ice from West Antarctica. We must have lost most of the ice from Greenland. And that combined equates to roughly 12 meters of sea level rise relative to today. And actually, we know that the melting of West Antarctica and Greenland during this period was probably asynchronous, so they wouldn't necessarily have all added up at the same time. So this is all kind of implicating the fact that we may have lost parts of East Antarctica too. Traditionally, East Antarctica has been thought to be relatively stable compared to West Antarctica, for example. Okay, so looking a bit more closely at this time period, what regions of Antarctica might have contributed to the sea level rise that we think occurred during the mid-Pliocene? So on the left here is just a figure showing temperature relative to modern during the mid-Pliocene Warm Period. And we can see many features of this warming environment are what we're expected to see in the coming decades. So we see there's a clear polar amplification. We see warming isn't uniform. There's not so much change around the equator. We have significant warming happening over North America and Greenland. And we also have really significant warming over West Antarctica and also regions of East Antarctica. And so if we move over to this figure on the right, we can see that these regions of warming coincide with, so this is a representation of Antarctica's elevation if we were to remove all the ice, so it's just the bedrock exposed. You can see that, so the blue colors represent, I should say, elevations below sea level, and the red colors indicate elevations above sea level. And so we can see that large portions of West Antarctica sitting below sea level, but also there are these regions in East Antarctica which also rest below sea level. And that's significant because we think that marine terminating ice sheets resting below sea level in Antarctica, or anywhere for that matter, could be particularly susceptible to melting in a warming world. And now, To date, there's been a lot of attention given to the possibility that West Antarctica might have begun melting back, potentially irreversibly in the long term. But also there's this increasing attention being given to these regions of East Antarctica. For example, the Aurora subglacial basin and Wilkes subglacial basin, and the potential impact of warming in these regions. So I've said previously that there's some kind of indirect evidence from sea level reconstructions that we lost parts of certainly West Antarctica and potentially East Antarctica during the Pliocene. But actually models don't do a fantastic job at reconstructing this. So there isn't much agreement in models as to how much or if at all East Antarctica melted back during this period. And so here I'm just showing a recent example of a model that was able to reconstruct retreats in East Antarctica and in the Aurora and the Wilkes subglacial basins. And to achieve this, this model had to include processes which are still, as far as I gather, somewhat contentious. So things like marine ice cliff instability and hydrofraction, sorry. And I think it's still contentious to say as to whether or not they'd actually operate in the real world in the future. Although there are others in ACEAS who know much more about that than me. So what about paleo data? So there's also some conflicting interpretations of the available paleo evidence from this time period. So taking a step back, we know that during other periods of large ice sheet collapse, one feature found in the paleo record is evidence for the production of large amounts of icebergs. So an example of that was during the end of the last ice age, when large marine terminating ice sheets on Europe and North America were melting back comparatively rapidly. We saw evidence for large iceberg outburst events or discharge events, iceberg armadas, as it's being referred to in this paper title, which I quite enjoy. And so there is evidence for these large iceberg discharge events emanating from East Antarctica during the mid-Pliocene. But because we can't precisely place when these events occur in time, or it's difficult to place exactly when these events occurred, there's still some debate about whether they represent retreat or collapse of ice sheets due to warming, or if in fact they represent coincide with intervals of cooling sea surface temperatures. And actually what we're seeing recorded is suppression of melting of icebergs, which is allowing them to travel further. So there's still a little bit of a debate about what exactly these iceberg discharge events might be telling us. So with all that in mind, the overarching aim then of this project is to reassess whether sensitive areas of East Antarctic ice sheet underwent periods of enhanced ice loss groups during the mid-Pliocene, and if possible to link these events to the warmer climate during the mid-Pliocene warm period. Okay, so that's all well and good, but obviously we're going to need, well, how might we go about achieving these objectives? Obviously we need some record of past climate spanning the mid-Pliocene warm period. And so I'm just using this as an example because I'm sure many of you are familiar with ice cores and the fantastic records of past climate that they hold. But unfortunately, these ice cores only reach back as far as the last 800,000 years. And so there's a lot of effort being put in at the moment by researchers at IMAS and elsewhere working on trying to extend these records even further back in time. But there isn't really any prospect of drilling ice as far back as the mid-Pliocene warm period, which was over 3 million years ago. So instead, we turn to other archives of our past climate in the form of marine settlement cores. So in the same way that snow and ice is deposited in layers on top of an ice sheet, sediments are slowly accumulating on the seafloor over time. And just the same way that ice cores can provide valuable archives of past climate, coring down or drilling down into these sediments can provide us with useful climate records. And so I've just included up here some examples of how we might go about accessing these sediments. So in the center here is with the most low-tech, or one of the most low-tech looking examples. It's just a simple Bragg box corer. We also have more advanced techniques such as gravity coring or piston coring, which allow us to retrieve longer cores spanning sort of tens of meters. And then we have kind of the gold standard of paleo archives, which is complex drilling operations which are capable of recovering really long cores spanning kind of kilometers in length, up to kilometers in length. So here's just a few images kind of showing sediment coring in action, which took on a voyage back in 2018. So on the left, you can see lying horizontally the sediment corer, which is about to be lowered over the side. In the center here, we have an example of a core which has just been retrieved. The plastic lining is being pulled out of the corer, and we're splitting that into core sections, which are more manageable. And then on the right here is just an example of one of those sections which we've split open, and you can see the kind of alternating sediment layers in there, which I was talking about. And so for the work that I'm doing with ACEAS, I'm actually using legacy core material, which was drilled by the International Ocean Discovery Programme way back in 2000, the year 2000. And this is one of these large drill cores that I kind of mentioned previously, and actually totals a length of 999 meters, so 1 meter short of a kilometer. So rather than going out and collecting these cores for this project, as I say, I'm working on legacy core material, which actually arrived in this state last week. So I now have samples sat waiting on my desk here at IMAX, which is great. And so some background on the site that I'm going to be working on. It's this site, ODP 1164 is its designation. It was drilled on the Antarctic continental margin just offshore of Wilkes Bay. And the sediments deposited at this site have been eroded and transported by ice from the Antarctic continental interior. And so by examining these sediments, we hope that we can gain insight into past ice sheet dynamics. It's kind of summarized just on the right here. There's essentially two primary sources of original sediment at the site. So we have a local source in the Lambert-Amory ice shelf system, and we also have some more distal sources being transported via the Antarctic slope current or the Antarctic coastal current from further afield in East Antarctica. Okay, so as I say, this core is nearly a kilometre in length. And unfortunately, I'm not investigating the entire core. That would take a long time. Instead, I'm focusing on parts of the upper 40 meters or so. And so a really important part of any paleoclimate, or especially paleoceanography study, is being able to date our sediments and being able to determine when they're being deposited. And that's especially true for this study where I'm trying to target a specific interval in the mid-Pliocene Warm Period, which wasn't a hugely long period of time. So initial dating of these sections of core has been performed using looking at microfossil assemblages. So we know when certain microfossils lived and when they went extinct, and that gives us some dating horizons. And then there's also some magnetic measurements which we made, which records past flips and reversals in Earth's magnetic field. So magnetic minerals kind of operate like a little mini microscopic compass, and as they're being deposited, they become aligned with the Earth's magnetic field at the time that the sediments are deposited, and then we can measure that and determine the polarity of the Earth's field. And we know when that reversed in the past. So what's kind of exciting about this core, especially is if you just look on the right-hand side, this is just a figure showing the polarity of its core site for the upper 55 meters, with some dates on here. What we can see is that there's a really expanded core section between approximately 3 million and 3.6 million years ago. And that coincides with the timing of the Pliocene Warm Period. And so that kind of makes this core a really, a potentially really fantastic archive to look at, to investigate this period. So as I say, one of the goals is kind of constraining when the mid-Pliocene warm period exactly occurred in the eastern sediments, and whereabouts, like which core sections that spans. And so we know that its approximate location in the core based on these previous dating of the sediments, but there's a little bit of wiggle room in those dates, and sedimentation isn't always linear, and so we're really trying to work on constraining when the mid-Pliocene warm period was using other techniques. And so that takes me to this technique. So I'm using some new X-ray fluorescence measurements taken on this core to identify the mid-Pliocene warm period. So X-ray fluorescence, or XRF, provides information on the chemical makeup of sediments within the core at a really high resolution, like up to sub-centimeter scale, which is great. And although it's not strictly quantitative, it's a good indicator of the relative abundance of different elements within the core. It's rapid, it's non-destructive, so it's a really ideal technique to use on sediment cores like this, which are really valuable legacy material, which we want to be as we want to destroy as little sediment as possible, essentially. So really briefly, the way that this XRF analysis works is this photons are fired from an X-ray source, kind of shown here on the left. An element-specific fluorescence is then emitted, and we measure that fluorescence at a detector, and that allows us to determine the relative abundance of a whole range of different elements in a sediment and how they change through the sediment core. So this technique is really well established. It has a whole host of applications, and this data set will be used for other things as well, but for now we're mostly interested in the ratio of the elements of barium and titanium in the sediment core. So how exactly is knowing the ratio of barium and titanium in these sediments going to help us in constraining when the mid-Pliocene warm period was? Well, the ratio of barium to titanium in especially Antarctic sediments reflects the abundance of the mineral barite. Now, barite forms, or barite formation, I should say, in sediments reflects the supply of organic matter within the sediment. So increased fluxes of organic matter typically lead to increased formation of barite, which will give us a higher barium to titanium signal. And so often in paleoceanography studies, a high barium to titanium ratio in sediments is used as, or is interpreted as reflecting higher surface ocean productivity at the time that the sediment was deposited. Now, over long time periods, and especially on the Antarctic margin, higher surface ocean productivity can indicate periods of warmth, essentially. Warmer conditions leads generally to higher productivity. And actually, this is arguably our best proxy for changes in productivity on the Antarctic margin, I should say. Okay, so all that being said, high barium titanium, high productivity, warmth. That gives us our method for constraining Pliocene warmth. And so here is the barium to titanium records for the sections of core that I'm interested in. So just to get your eye in on the x-axis here, now we're looking at core depth in meters below sea level. So we're going from sort of 18 meters down to 38 meters. And on the y-axis, as I mentioned, is this barium titanium ratio. At the top, I've included some of these preliminary, or some of the original dates of these sediments. And then, yeah, in green is the barium titanium record. And so you can see we go from a period of relative low productivity to a high period to low period. And then we have this period of greatly increased productivity, slight decrease, and then an increase again. And so based on these new data, we think the mid-Pliocene in this core section probably spans this interval shown here. So certainly these two peaks, I think, coincide with warming during the Pliocene, during the mid-Pliocene. There's also some other indications from these sediments that maybe it stretches back as far as here as well. So this kind of gives us two bits of information, as I've kind of been stressing. We know exactly whereabouts in the sediment core now corresponds to mid-Pliocene warm periods, but we also know within that which intervals correspond to relatively warmer periods and relatively cooler periods. And so this allows us to relate past iceberg discharge events, which I mentioned earlier, recorded at this core site, to the environmental conditions around East Antarctica at that time. So was it warmer, was it cooler? Okay, so far I've kind of alluded to the fact that we have evidence for past iceberg discharge events in the Southern Ocean and elsewhere, but how can we actually identify the presence of icebergs which are in the surface ocean in the sedimentary record? Well, as kind of shown on this schematic image on the left here, icebergs often carry with them sediment eroded from the bedrock beneath the ice sheet where they originate from. And as that iceberg travels through the ocean, it melts over time, and this, what we call iceberg grafted debris, or IRD, is rained out on the seafloor. Kind of see in this figure here how it's kind of forming layers in the sedimentary record. So as I say, these are known as iceberg grafted debris, and they really stick out when we analyze sediment core like this, because they're made up of sediment grains that are essentially too large to have been transported by ocean currents, and so really the only way that they could have arrived at the core site are via icebergs. So typically we're looking at grains bigger than, say, 250 microns, or even bigger than 2 millimeters, where you can even get huge kind of cobbles and boulders being eroded and deposited, which are not so easy to core into. So, okay, the next question then, if we can identify these iceberg discharge events in our sediment, is whereabouts are these IRD sediments coming from? So they're telling us something about, so in the example of this core site in the Lambert-Amory region, or just offshore from the Lambert-Amory, are they telling us something about local ice sheet dynamics there, or are they telling us something about a more distal signal from elsewhere in East Antarctica? And so to answer that, we look in detail at exactly the sediments that are making up these iceberg debris, and we relate those sediments to onshore geology at different source regions around Antarctica. So thinking about East Antarctica in particular, geology in East Antarctica is kind of broadly split into several large terrains, which formed at different times in the past, kind of as shown on the right here. And actually, if I just slide this along, you can kind of see where those coloured geological terrains relate to. And you can see that the regions that we've previously identified as being potentially at risk of retreat in the future, and in the past during the Pliocene, the Aurora subglacial basin and the Wilkes subglacial basin, they have kind of differing geologies from one another, and they also have different geology from the local region. Well, it's quite a large local region, but the region being drained by the Lambert-Amory ice shelf system. And that's really useful if you want to fingerprint where these sediments are coming from, these iceberg sediments. So by picking out and analysing the chemistry of specific minerals in the sediment, as I say, we're able to determine when they're formed. We actually were able to determine when these minerals are formed. And it's that information, the time of formation of the minerals, that we can then relate back to our East Antarctic geology. And so in the example that I'm going to kind of show you here, This is from previous work measuring the dates of formation of specific minerals in IRD layers, which are these on the left here, hornblende, they're called. It's a very common occurring mineral. And so what this previous work showed is that by dating sediment cores and on-core outcrop, geology outcrops, dating the hornblende grains found there, you can see that there's this regional pattern of around the Adélie Land coast, a cluster of grains that date around 1.5 billion years old, a cluster of grains from the Wilkes Land margin, around 1.1-ish billion years old, and then the local geology around the Wilkes Base region, they were formed around 500 million years ago. So quite distinct individual populations, which is great. And so this technique has been applied previously to the sediments at this core site, and they were able to show that during the Pliocene, there was indeed an increase in the amount of iceberg grafting of sediment sourced in the Aurora subglacial basin, this ASB here. So we have a peak in our local source 500 million years ago, and then we also have this peak which has been traced back to the Aurora subglacial basin of 1.1 billion years ago. But because of some uncertainties in the stratigraphy, it wasn't really possible to definitely tell whether these iceberg grafting events originating in the Aurora subglacial basin were related definitively to periods of warmth, or whether, as I mentioned previously, they actually represent just slightly cooler sea surface temperatures and more distally traveled icebergs. And that actually was what was argued in this paper. Just jumped ahead there, spoilers. So now that we're able to constrain both the timing of the Pliocene Warm Period and the environmental conditions at this core site, using this new XRF data, we're able to determine whether or not these iceberg grafting events actually do relate to warming and a potential retreat of the Aurora subglacial basin. And so, probably see where this is going, but yes, we find that actually, increases in iceberg discharges from the Aurora subglacial basin do coincide with intervals of warming along the Antarctic margin, as interpreted from our XRF record, shown again here in green. So on this figure, I'm showing, as I say, in green, the relative abundance, so the ratio of barium to titanium, where again up indicates warmer conditions. And then in blue, it's maybe a little hard to make out, but this represents histograms of the proportion of iceberg grafted hornblende grains sourced in the Aurora subglacial basin. And we can see that there's variability through time, but during these periods of peak warmth, we see an increase in the proportion of IRD coming from that region. Just on the right here, I've plotted up a cross plot showing the XRF barium titanium data. So to the right indicates warming, and percent of IRD sourced in this region, this subglacial basin. And you can see there's a good correlation between the two. So that kind of summarizes the sort of preliminary work that we've done on this course so far, reinterpreting some of these previous records. And just to leave you with some sort of preliminary takeaways. So, yeah, we've seen that, yes, large iceberg discharge events did coincide with intervals of warmth during the Pliocene. And so I guess the biggest takeaway is that this indicates that during warming comparable to medium to high emission scenarios, yes, there is good evidence that the Aurora subglacial basin experienced potentially significant ice mass loss. And so obviously that has ramifications for future warming. Bearing in mind this is a period that's warmer by 2 to 4 degrees, and we're already at 1 degree. So now I'm not necessarily saying that we're going to experience a retreat or a collapse of the Aurora basin in the 21st century, as that would occur on timescales of at least probably centuries, and ditto for West Antarctica. But the point that I'm trying to get across is that if we do push our climate system towards this 2 to 4 degrees warming, we could be kind of locking ourselves in for some significant sea level rise a bit further down the line. And once that train leaves the station, then there might not be any way of stopping it if these ice sheets do start to rapidly retreat. And so, just the final sort of slide I wanted to leave you with was this point that these so-called low likelihood, high impact scenarios of sea level rise in the future, which is discussed a lot in the latest IPCC assessment, all of the IPCC assessments. These all hinge on the response of Greenland, West Antarctica, and potentially East Antarctica to future warming. And so on the right here, again, it's a bit hard to see, but basically we have projected sea level rise for looking further ahead into the future now, the year 2300, relative to modern or pre-industrial. And some of these kind of upper limits, the text you probably can't read here says, it can't be ruled out that under certain scenarios, in the higher emission scenarios, we could be looking at up to 15 meters sea level rise. I think that's kind of a direct link to the fact that we think we had significant ice mass loss during the Pliocene Warm Period. And so maybe we, if we continue along the road of mid to high emissions, which currently we're kind of on, maybe these low likelihood, high impact scenarios are something that should be taken into consideration for our, geologically speaking, not too distant future. Cool, I think I'll just leave it there. I'd be happy to take any questions.
Thank you, Tom. Nathan has a couple questions in the chat, and maybe you can just read them off your computer.
I can talk to it if you like, Tom.
Okay, yeah, that'd be great. Thank you.
Yeah, so have I understood correctly that at different times you've had armadas of ice debris, and yet if I look at East Antarctica currently, it's one contiguous ice sheet, so all areas should deliver up lots of ice debris, I would have thought, at the same time. So it seems odd to me that at different times you've got different source regions of debris.
Yeah, so for a little bit, I can just get my slides back up. So for example, looking at this plot here, if we just ignore the green, just look at the histograms of IRD source. So actually the core top, I want to have a look at the core top values from this core site are around 20 to 30% icebergs coming from the Wilkes margin. So there is like a background level of IRD coming around from East Antarctica to this core site. And as you say, it's kind of a jumble of icebergs coming from all over the place. But what's different about these warm intervals, and has been suggested from other locations in Earth's past, is when you have specific areas that undergo really rapid ice mass loss. So I use the example of the collapse of ice sheets in the Northern Hemisphere during the last deglaciation. When you have these really large retreats happening from specific regions, then you end up with huge calving events happening repeatedly. And so that kind of swamps the signal of other regions. Does that kind of answer your question?
Yeah, it does. I'm just surprised that some regions collapse so much more rapidly than other regions when they're almost in the same climate.
Yeah. It's interesting that, I mean, these two regions that I've been referring to in this talk, kind of being suggested as potentially more susceptible than other regions. Yeah, because they're these basins sit below sea level, they're on a reverse slope. So they might be more susceptible to sort of rapid, yeah, I don't want to include sort of time scales on here, but they might be more susceptible to collapse, essentially.
Yeah, okay, yeah, I think that's a good point about the reverse slope and the instability. Thank you, thank you.
Cheers.
Tom, I'm just wondering if you've had a chance to look at, or you plan to look at some of the ice sheet model reconstructions of the Continental Pollard or Townsend Edwards or any other ones that might have occurred. I mean, I dare say there's a very large amount of uncertainty in terms of what will govern the timing of the retreat in those models, in terms of the forcing from the ocean in particular.
Yeah.
But I just wonder if you're thinking about having a look at that.
I definitely am. I'd say I haven't dug too much into that as of yet. My understanding is that, yeah, there's quite a bit of variability about agreement amongst the models, but I haven't looked individually at their responses. It'd be interesting to see. I kind of alluded to this. There's a recent paper by Chris Stokes and others looking at this time period amongst others. And in their model, they did they were able to recreate this retreat, but they had to include these. I don't know if they're contentious or not. Sort of feedbacks of ice cliff instability, and yeah. So yeah, I want to dig more into that, definitely.
They're definitely contentious. Yeah.
Okay, they are.
Yeah, and that's the point. So Townsend Edwards, I think, has shown that you can reproduce. You don't need to invoke the marine ice cliff instability in order to capture Pliocene retreat.
Okay.
But it requires a certain model setup in order to do that. So it's contentious, but it's not, and it's not required.
It's not the only way. Okay.
Yeah.
Yeah, and now I need to look more into that for sure. Yeah.
Yeah, and thanks for the great talk, Tom. Very elegant work on a pretty special core. Just a question, it might be a bit ignorant of me, about the chemistry, the biology, how titanium and barium relate to productivity. Are they contained in the phytoplankton and then rain out as the...
Pretty much that's it. So the reason, first of all, that we ratio these elements to titanium is because, like, a lot of these elements are contained in terrigenous material, which is being eroded and supplied from the continent. And so we kind of normalize that by ratioing to titanium, because that's a common element that basically just comes from these detrital sediments. So that's kind of why we look at titanium. Barium, yeah, it's taken up by phytoplankton, pythons, and other organisms. And then I think it's still, as far as I'm aware, it's still a little bit uncertain exactly the processes that lead to barite formation from that. Some people think it's like mainly microbially mediated. But yeah, essentially you have the barium that's taken up by the organisms. And as they decompose on the seafloor, barite's formed, which is then more stable essentially as a mineral. Yeah, so it's just taken up by the organisms essentially.
Thank you.
Cheers.
So Ilko, you have your hand up?
Yeah, I was going to point out that, you know, the emphasis on the middle Pliocene is of course interesting, but when you start talking about the future, we're already beyond it, right? So middle Pliocene CO2 set somewhere about 350 to 400. We're well above that already. And if you look at even the low emission scenarios for the future, that we're going to be much higher than that. We're actually going into Miocene territory in terms of CO2. The issue we have, I think, with that is that, you know, the middle Miocene, the Antarctic ice sheet, is potentially much smaller than it has been for a very long time, since it actually started to form for 34 million years ago. And so I think what you're finding for the Pliocene is a very interesting indication, but the implication would be if we actually kept the atmospheric concentrations where they are now for sufficient long time, that might actually start to become if you want, the analog. When you're talking about looking at mid-range emission scenarios, I think the situation would be a lot more dire if we keep them there, right? So my feeling would be that, there was some discussion there about modeling the mid-Pliocene, etc. It would be very interesting to start to think that through a bit more and go further and see what would need to happen for melting back onto land, right? So we're now continuously talking about the sort of more marine-based bits of the ice sheet. If and when we start thinking about this in terms of modeling, we may have to start thinking, okay, well, can we continue that and go more into land-based melting?
Yeah,
Just
that's
an
a really
observation.
yeah, that's a really great observation. It's a really great point. Yeah, we're already at these CO2 levels, definitely. And yeah, even if we stopped emitting CO2 today, would we eventually reach the 2 to 4 degree warming of the Pliocene? The thought did cross my mind when I started this project that it's almost too late to start looking at the Pliocene. But yeah, I think, yeah, moving forward, like, yeah, thinking about these the potential for terrestrial melting as well is like equally as important. I don't think there's much physical paleo data available on like terrestrial retreat, unfortunately. But yeah. Yeah,
it's a big problem, right? But we have only 2 big warmings in the paleo record that we can look at. One is the mid-Pliocene, which is a reasonable warming, and then we have the transition into the mid-Miocene warm period. I think those warmings would be more useful to look at, as you are doing, than the cooling trajectory because of hysteresis in the ice sheet behavior. The other thing that I think what we're beginning to see is that the ice sheet responses are, the forcings are this very long-term process, and the ice sheet responses seem to be quite stepwise. So I think there's quite a lot missing, and it's not all about ice shelves and how they disintegrate. We have to start thinking how could that continue? And I think if we start modeling this, we need to go further and start continuing those runs into how bad can it get.
That's really good to hear your perspective. Thanks, Albert.
I think we have time for one quick question from Roland. You've got your hand up.
Hi, yeah, fascinating talk, and I tend to agree with Elko about relevance of our CO2 levels for where we might be heading. Probably back to when the dominant life forms were cyanobacteria or something. My question was in terms of completing this this climate record in your mid-Pliocene core. Are there prospects of using the X-ray approach to look for carbon dioxide concentrations? It's outside my area of excellence, but things like boron come to mind.
Yeah, so boron's really commonly used, or it is used to reconstruct CO2. For that, you need, boron's usually measured on foraminifera, which we don't really have in this core. There was a recent reconstruction spanning this time period, published 2 years ago now, where they had like comparatively high resolution CO2 records, which we can compare to. But yeah, measuring CO2 ourselves, we probably can't do that at this core site, but it has been done elsewhere.
Okay, so it can't just be done on the analysis of the bulk samples, the way you've been doing in barium.
No, unfortunately not. No. Yeah, not currently anyway. That would be great if it's possible.
Okay, thank you.
Okay, well, thank you, Tom. Give him one more. Thank you everyone for coming, and thanks everyone online for coming as well. Yeah, we'll see you at the next ACEAS seminar.
Awesome.